Ladies and gentlemen, today we shall be dealing with electric currents. Electric current. So now, what is electric current? What do you understand by the term electric current? Why do we have electric current? Why do electric current exist? How does it happen? How are they produced? So in this video, you try to determine or you try to understand the concepts of electric current. So I'd like you to stay with me to the end of this video. So now, electric current. Now, okay, let's take for instance a conductor. This is a conductor. This is a negative pole and this is a positive pole. Now, for instance, let's compare electricity to water system. Now, if we have let me say here I have my reservoir, that's my tank, then an outlet here. So the outlet here led to a tap. So the tap is like this. That's the tap. Now, okay, that's the tap. So, and here I have a full tank here. I have a full tank here. Then the valve of this tap is locked. Now, if the valve of this tap is locked, does it mean there is no water in this pipe? Of course, there is water. So, actually, there is water in the pipe. It's just that the water there, they are not moving. They are static. They are not going anywhere. They are just where they are. Why? Because the valve of this thing is locked. Is locked. The valve of the tap is locked. Now, this is the water system. Now, this water are in the pipe, it's just that they're not moving. So even though there is a bucket of water here, even there is a bucket here, empty bucket, and I'm to fill it with water, provided this tap, the valve of the tap is still locked, then no water will be filled there, right? Same thing applies to our conductors. Let me draw another one. Sorry. Same thing applies to our conductors. The negative pole, positive. Same thing applies. Now, this place is when there is no movement. So once there is no movement, all these water molecules they move in an haphazard motion. In the sense that they move anyhow, they collide with each other and just move anyhow. So here we have something like this, moving whichever direction they choose to move. Same thing happens in the pipe. So they just move anyhow. They don't have a specific direction they are moving towards. So they are just the way they are in the tap. Not going anywhere. They're not moving back, not moving forward. They are just there. All what they do is collide with the wall of the container or the pipe and just make a random motion there. That's what they do. So what happens? Once I unlock the valve of the tap, once I open it, what happens? Water comes out, right? And when water comes out, what happens? This bucket is likely to be filled. But once I open this thing, everything moves in this direction. In that case, this valve brought about a kind of force that make the water to flow in a single direction. I'm trying to explain the analogy between electric currents and the water system. Now, electricity is actually derived from movement of electron. Electricity is derived from what? From movement or from moving electron. It's derived from moving electron. Now, for every conductors, there's always have a chemistry basis for their conductance. Are you getting it? So in the case where we have sodium as a metal, it conducts electricity because it has an extra what? An extra electron in the atmosphere, which enables free what? Mobile electron. So the major thing that enables elements to conduct electricity is the free movement of electrons in the atmosphere. So this sodium can combine with chlorine and make a normal source conduct electricity when it is in solution because of what? There are free mobile electrons moving in the atmosphere of the metal. So meaning electron is responsible for the movement of electron rather is responsible for the conductance of any metal or any conductor. So everything that are inside this thing, they are electrons negatively charged. They are negatively charged. But it's just that they move whichever way they choose to move whenever there is no movement, or let me say whenever there is no potential difference acting there. So the pressure of the water here, causing it to move in a specific direction is actually the voltage here. It's actually let me say, put it in brackets here. It's actually the voltage when it comes to electric current. So here we have flow of water, but here we have what? Flow of electron. So they have so much similarities. So the valve of this thing here, the valve of this tap here, it represents the switch in the electrical system. So whenever the switch is opened, for instance, I have my bulb now. This bulb is not powered. Why is it not powered? Because those electrons in the conductor are just moving anyhow. They don't have a specific direction to move. And for any electric current to be produced, definitely potential difference must come in. And for potential difference to come in, there must be a coordination of the electrons to move in a single direction. So if those electrons don't move in the same direction, then there cannot be production of any electric current. So now this switch is opened now, and now there is no light. So when in that case all these things are not moving, they are not moving in a specific direction, they are just static. And once I open the key, once I close it rather, what happens? It powers it, because immediately I close it, what happens? Immediately I close the key, what happens? There was a kind of condition that, okay, electrons, everybody come in order and let's go and power the bulb. And that's the work of the potential difference. That's the voltage in the system. So the brightness of the bulb depends on the potential difference. That's the force driving the electron in the conductors. So as it is closed, as it is open now, they are not conducting, they are just moving anyhow. So in that case, they don't have the capacity to power any form of gadget or appliance. But in this case now, when it was opened, what happened? This thing wasn't filled, so it can't power anything. It can't produce, it can't bring it without any result. But now that it is closed, it is able to fill in the bucket, and we can now say, I fetched the water. It has done the work. I hope that is clear. So that is the analogy between water flow and electron flow. So electron flow is referred to as moving electricity is derived from the term moving electrons, and that's why it's best explained when it is used with the with water system. And that's that about that. Now let's move forward. So now this is it. There is no movement. There is no potential difference here. They're just moving randomly. and there's potential difference. Now, why do you think they are not moving towards the positive charge? It is just because these electrons, they are negatively charged. And law of static electric charge states that was like poles repel while unlike poles attract. Electron will repel with this negative pole here, and it will attract driven towards the positive pole here. So this flow is actually referred to the what? This flow is actually referred to the what? Electron flow. Is referred to the what? To the electron flow. Is referred to the what? To the what? Electron flow. But do you now know what? Electron flows like this, but current flows like this. But what? Current flows like this. So this one is referred to as current flow. I will explain the concept. Current flow. Now, you now be thinking, how come electron flows this way from negative to the positive pole, and currents now flow in the reverse case? What's happening? What's going on? Let me have a bold. So to be easier to understand, positive pole, negative pole, 1, 2, 3, 4, 5, 6. So like this, like this, like this, like this, like this, like this. So this is referred to as what? Electron flow. Electron flow. And this one is referred to as what? Current flow. You now be thinking, electrons are moving this way, why is now current moving in the reverse direction? Now that's the point. Now, let's take for instance, you have a body of C. A body of C. And on it is a canoe. Let's take for instance, you are in the canoe. Now this is you seated. Yeah. Now you now have two pedals. This is the first pedal, and the second one is on the other side. Now you want to move in this direction, and this one is water. Now mind you, when we were doing the analogy, water was representing electron, right? I said the water in the pipe will be moving anywhere. Same thing as the electron in the conductor that is opened will also be moving anywhere. So in this case, this water is representing the what? Electron. Why you here that wants to do the real work, huh? This one is actually a meter, but you here, you are representing the current. So for current to flow, what happens? Water must be pedaled in this direction. So if water is being pedaled in this direction, in the reverse direction, what happens? Your boat moves this way, whereby moving you originally. So you are representing the current. Let me do it like this. So you are representing the what? The current. So as the electrons are moving in this direction, what happens? The electric current is moving in. So this kind of flow is also referred to as what? The conventional flow. I hope this concept is clear. So electric currents are actually produced when electrons are coordinated to move in a single direction. And once they move in a single direction, if they move due east, current to move due west. If they move due north, current to move due south. Opposite direction. That's the conventional flow. Just as this analogy has explained that properly. So the water the sea itself represents the electron. While you and your boat, everything, you represent the current. So for current to move in this direction, your water, the sea body, the water itself must be coordinated to move in the reverse direction for you to move. I hope this is clear. Because just as this man in this place cannot pedal the boat like this, and the boat will also move the same direction. Never. They always move in the what? In the opposite direction. I hope that is clear. So that's that about what? About production of electric current in the metallic conductor. So let's talk about Factors which electric current depend on. Factors which electric currents depend on. Now, number one is the drift velocity. Drift velocity. Now that's the velocity at which what all these the electrons in the conductor move it. Is the drift velocity. Another one is the charge per volume. Per volume. The third one is the surface area of the conductor. And the fourth one is the electron. Electron itself. So all these four things are the factors what currents depend on to be produced. So this is represented with a V, this is represented with an N. That's the number of charge per volume. Sorry. This is V. Okay, yes, number of charge per volume. Then this one is the surface area. This one is the amount of electron in the conductor. So therefore it brings about a formula which says my high current is equal to N AVA. That's the number of charge per volume times surface area times the drift velocity of the electron times the amount of electron in the conductor per unit what in the conductor rather. So it's brought about this formula. At the same time, electric current may be also defined or is referred to as the what? To as the quantity of charge per unit, as the quantity of charge moved per unit time taken. I can say it's the rate of quantity of charges with time. So which brought about the formula Q over T. So current is what can be defined as the rate of change of quantity of what charges in the metallic conductor. And that's the evidence. And there's something we call the current density. The current density is represented with a J. And this J is equal to my current over what? Area. So from here I can see my J is equal to what's my current? My current here is equal to what? Is equal to NAVE. NAVE all over my area. So area cancels area. So I can now say my current density can also be equal to what? NVE. So that's the electric current. And just don't forget that the force that is responsible for the movement of electrons from the negative pole to the positive pole is referred to as what? So as the potential difference. So potential difference, which is also referred to as what? The voltage. The voltage which is represented with a V, and also the unit. The unit is volts. Also what? A V. Yeah, also a V. So potential difference is the force that is responsible for the movement of electrons in the metallic conductor for the production of what? Of electric current. So that's all about today's class. And don't forget to subscribe to this channel, like and comment below your opinions and your views, and don't forget to press the bell icon and in order to be notified whenever new classes are being uploaded. So we are there for you. Just a few months. We are there for you. So thank you very much. Meet you in our next class. Love you.